Okay. 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 Now let's continue from our last lectures, okay, on the boost converter. All right. So I say the boost converter actually step up the wattage, okay, a lower wattage to a higher wattage. All right. And again, it is based on the inductor, okay, to actually help to increase the wattage. So the operating principle side is actually the same. Okay, there's always a one on state, charge the inductor, off state, discharge, okay, the inductor, or vice versa. And then the controlling of the charge discharge is basically, okay, based on the duty cycle, okay, that is going to pulse the transistor. And then, of course, the duty cycle will actually control, okay, the wattage, how much wattage you want to boost. But this is just an open loop system, meaning that, it's not a feedback system. So in real application, there's always a feedback system. Okay, so again, this will show the inductor's current, which actually indicate the charge and discharge, okay, of the inductor. And the voltage, capacitor voltage, will be the output voltage. In this case, is 12 volt. Our input is 5 volt. Okay, you can actually boost it up to 12 volt. Okay, and then of course, for buck boost, okay, buck boost converter, they do have this critical inductance value. Okay, which will tell you what are the lowest or smallest value you can use for this given switching frequency. Always remember, the higher the switching frequency, the higher the switching losses. Okay, and then the advantage of higher switching frequency is that it will make the inductor smaller in size. Okay, and of course, smaller means cheaper, right? And also smaller size as well. So you need to really look into, okay, which one you want. Obviously, for low power supply, okay, low power supply, usually they will have a very high switching frequency because when your power is low, the switching loss is also low. Okay, that is what happening to many of the commercial power supply. And of course, we also study the gain. Okay, we always look at the gain, the critical inductance, and the input resistance of a given, what we call these are converters. All right. Okay. Now, of course, efficiency again is always the measure of the, the output power over the input power. And then these are tutorials, so please do it at home. And I also show the feedback control. Okay, feedback control is always the output, okay, minus the references. And then go to the PI control, and then to the duty cycle, okay, and then to control the switching. So here I will show you one of the example here, okay. Okay, the MATLAB examples, all right. So you can set, okay, as we see here, our input, okay, it's only 5 volt, all right. And then we want to boost it up to 12 volt. So the reference here, we set to 12 volt. So when you run for 0.1 seconds, okay, so you will have the output of, okay, 12 volt. Oh, still running, huh? Okay. Okay, yeah. It will achieve 12 volt, okay, for the output, and double click. And you can see this is the output voltage. All right, so for PI, I use a manual tuning method lah. Okay, for this one. So I obtain 0.001 and 10 of I in order to get this. Okay, remember, this P and I value, right, is not applicable for voltage maybe higher than 15 watt or more. Okay, if you have, like, for example, let's say I simply click, oh, now I want to go to 18 volt. Okay, but I didn't change the PI. So there are limits, okay, for the PI. So make sure that you know your buck or the boost converter operating range so that you can set your P and I accordingly. Okay, now you see when I put 18 volt, you see, it oscillates. It becomes bigger and bigger and bigger. So meaning that I need to reduce the I and the P in order for me to achieve 18 watt. Otherwise, you see, this is considered oscillate already. But if I change this to a smaller value, let's say 9 volt, still in a buck, right? But this P and I value, okay, can handle this. Okay. Okay, it can handle this. So you can see, no problem, all right? No overshoot. Okay, it will give you a nice 9 volt, all right? So this will tell you that even you have a feedback control, okay, be it buck converter also same, doesn't mean that you set this voltage and you can set any voltage, okay, that you want, especially for the boost, because theoretically boost can boost up infinitely, okay. So for example, when I design this, okay, I set my PI based on 12 watt. So for 9 watt, okay, maybe 15 watt also okay, okay, 15 watt should be okay. But 18 watt is start to oscillate already. So meaning that if I want to, this boost to operate at 18 and above, I need to retune, okay, the PI value. Okay. So like I said, it's always a good, important to have experience of know how to tune it manually. Okay. Because not automatically all can tune one. I see 15 watt is still okay, right? But when I go 18 watt, it start to oscillate already. Okay. So that's about feedback control, okay, for the boost converter. Okay. So any questions?
No, sir.
Okay, thank you. All right, so no questions. We will move on. Okay. Okay, this is the commercial, like I said, boost converter. Very simple. When you see this black thing, this is the inductor. You can see the inductor can be as small as like the chip itself, So easily, this will operate like 100K kilohertz. Okay. And you see in the front, in the back, the circuit is here. And you see the inductor can be so small, 33 microhenry. So most of the converter I did last time, okay, usually it's high power. Easily, we want to have at least 5M and 3M of the inductor. Okay, so these are the inductor. Okay, and then of course boost converter also widely used in grid inverters. Okay, at the front end, okay, has MPPT to actually track, okay, the maximum power. Okay. So boost summary, okay, yeah, it can step up the voltage without using a transformer. Okay, and one thing is that the current, when the voltage go up, the current always low. Okay, and then the good thing is that the input current is continuous. Okay, unless your inductor are so small until the chances of working in the CCM is higher lah. Okay, okay, yeah, they have a higher current, okay, to flow through the transistor. Okay, because the transistor, when it turn on, right, is actually short circuit. Not say short circuit lah. I mean, the current will go here to charge so it's just like short circuit. So this transistor usually will need to withstand a higher current. And okay, like the output is very sensitive. Okay, especially up to 75% of the what we call this the gain here. Okay, 75%, you can see it go up very sharply because of this equation 1 over 1 minus D. So it will be much more, like I said just now, right? When I go up to 18 watt, right, it could become unstable, right? I need to retune the PI. As I voltage, I go above and above. Let's say I want to put 100 volt. So because of the PWM becomes so sensitive, like especially 0.9, maybe 0.91 and 0.92, it will have difference of 10 or 20 watt, Okay, so it become very difficult to control. That's why it's easily go out of what we call stability. So this, if you don't really tune, or you may need to have much more advanced type of controller, okay, to do that. So usually we will design them to operate within the range of 70%. Okay, so now we're done with the boost already. Okay, buck step down, boost step up. So the next one is called buck boost converter. So the buck and boost are joined together as a single word. So as the word says, so this converter can step down and also can step up. So you can do two things. Okay, so it provides voltage that can be lesser or greater. So it is actually work as like if your duty cycle is from 0 to 50%, okay, that is in the buck mode. And from 50% and onward to 100%, it is in the boost mode. Okay, so this is how it works. So you want to buck, okay, or you put 50% means that the input and output is the same. And then another features of this is that the output polarity is opposite of that input voltage. That means the plus minus is opposite. Okay, the polarity will change. So how this works again, you will notice that they are still the same 4 components. They are always inductor, capacitor is always there, and there is always one what we call this switching transistor and one diode. These are the 4 main. It just, they just arrange, okay, differently. All right. Okay, so from here, we will see that, okay, again, during the on state, what happened? Okay, the transistor turn on, right? It will charge the inductor. Okay, you see the inductor and the transistor chain place, right? Or for the boost, right? The inductor is on top, but now it's in parallel here. So it charge. Okay, so and then when it discharge, okay, off state. Now during the off state, okay, the positive and negative, okay, switch place. Okay, it switch place, and then this what we call this inductor, okay, energy store here will start to discharge. Okay, it will start to discharge. So that this diode you can see is in the reverse bias. So for this moment, your output, right, this will become plus, this will become minus. You see from here, all right, because of plus or minus here, because of this, okay, because of this, okay, when it turn on, okay, it charge, okay, it will start to charge this inductor. And then when it turn off, when it discharge, so the current will flow through it, and the polarity, this is how it will give you the polarity here. Now, for the buck and boost, right, the polarity is always plus on top, minus at the bottom. But for buck boost, it is opposite. So make sure that when you want to connect to the load, you have to know that the positive polarity is changed, okay, for a boost converter. And then similarly, okay, we come to the design. Now design, okay, to calculate the duty cycle, okay, we have to say that like, okay, the input is 5 volt, and then the V out is 12 volt. Okay, so you can see input is 5, output is 12. That is basically it will operate in the boost mode, right? Okay, so when you calculate, right, you will see it is always greater than 0.5. That means you are correct. If after calculation, right, it's less than 0.5 means you're wrong. Okay, if this is lesser, then you should have the value of duty cycle that's lesser than 0.5. Now switching frequency 20 kilohertz. Okay, same, these two are remain the same, and you just need to get the right equations. All right, and then you can calculate the inductor, okay, and the capacitor. Okay, so for DC-DC converter or buck boost or buck boost, right? The most important thing is still the inductor and capacitor. Okay, to get the right value so that they can smooth out the DC for you. Okay, so now we come to these examples. All right. Okay, we can actually implement them in what we call this MATLAB. So again, like I said, here calculation is 0.706. Okay, this is theory because we don't take into account of all the voltage drop. So after some adjustment, okay, I make 0.735. Okay, and then I will have the output. You can see the output is negative. Okay, negative 11.99, which is 12 volt lah. Okay, you can actually simulate that. Then of course the capacitor, I mean in the real circuit, you have to make sure the polarity is correct because here is plus, here is minus. Okay, here is plus, here is minus, so you will have a negative 12 volt output. And then, okay, so these are the inductor current. Okay, now you can see that the inductor current, right, is operating in the negative. Okay, in the negative current. Okay, the rest is the same. You can actually measure, they are peak to peak of 40%. So which is around, here is around 38, okay, or 39, okay, because it's 1 amp, right? So this one will be, the percentage. And then wattage, again, okay, 20%, all right, because you can see that it go to negative wattage. All right, it will go to negative wattage here, and then you can measure the peak, okay, 2%. All right. Okay. 1 amp, 2%. Because this is 12 volt, so it's roughly close to 2%. As mean from real measurement, right, you can actually validate that your inductor is correct. Of course, in real design, like I said, you can never get the value of 440 microhenry. You can only get 330 in the market. Okay, 330 microhenry, and you can get, I think the nearest should be 470. You can get 400 and this one. Okay, for the inductor, 33 or 47. And of course, this one capacitor, right, you only can get 100. And the 100 and above, I mean in the real component, only 220. So usually when you do real design, right, you will choose the one that is nearest to this. Like for example, you minus law, you take this one minus 100, difference is 47 microfarad. All right, and then you minus this one, 50 something around 50 over. So we take the one that has the smallest error. So we will usually take the 100. Okay. Okay, so this one, okay. Again, we always look into the three things, okay, the critical inductance, because of this, the value of the inductor, right, the real one, okay, will not fit. So we need to know what are the lowest value. Okay, what are the lowest value you can use? We always look at the critical inductance. Okay, similarly, critical inductance means that when it touches 0, okay, that is the lowest already. Or else like this one, see, it touches 0, it already don't have any charge or discharge. It wait for a while. Okay, that is DCM mode lah. Okay, discontinuous current mode. Okay, and again the gain. Okay, the gain is the negative law. All right, because of the change of polarity. Okay, instead of positive gain like a boost, but it is a negative gain. Okay, negative gain is minus D, okay, over 1 minus D. And again, the input impedance, okay, input impedance, they don't have negative, okay, because the impedance is always a positive value. So in this case, okay, this is how it looks like for the input impedance. So the input impedance will be almost infinity when your duty cycle, okay, is very, very low, okay. But as it go high, right, your input impedance will be almost near to zero, okay, will be almost near to zero. So again, we will try to operate, okay, maybe in within this range, okay, for stability. Okay, buck boost converter, okay. Okay, maybe I'll show you the MATLAB here first. Buck boost converter. Okay, so these examples, okay, can do it at home. Okay, I will spend more time on the flyback lah. Okay, because this one not really have any practical use for commercial. Okay, so you can see I get this wattage. You can actually see the the negative voltage of 12 volt. Okay, and then again, okay, you can do a feedback control as well. Okay, you can do a feedback control. Okay, you can do a feedback control. Okay, my input is how much? My input is 5 volt. Okay, then if I want to have 12 volt, okay, so I'll run. Bear in mind, because of the change of polarity, you see, you have to add them instead of minus. For buck and boost, you minus them, right? But because the voltage is already got negative sign, okay, so if you minus again, right, negative become positive, so it will give you error. So in this case, you need to put a plus here, make sure the only big difference here is the error is not minus because here already minus. Okay. Yeah, this one will run a bit slow, and because we are using this driver, more detailed model. The more detail you put in, the slower it runs lah. And it's not because of MATLAB is bad lah, because the solver, right? They have so many of them, and the solver is not just designed for solving this electronic power circuit, right? It's designed to solve all sort of different, model. So when there are so many models need to solve, so of course, the solver will be much more complicated as compared to Plex. Plex is only designed for power E, so it's eventually it's actually running much more faster. Like I say, I'm running only 0.1 second. It took roughly 1 minute. So okay, almost there already. Maybe I just click this one and you can see, yeah, almost reaches 12 volt. It's considered fast lah. I mean, if it's your real system, right? You just the moment you turn it on, it reaches 12 volt at 0.1 second. It's only because of the simulation here. It took a little bit of time. Okay. Yeah, almost there. Ampere also 1 amp. All right. So yeah, you can again, like I say, you don't simply like go to 24 watt or go very low. Okay, then your PI may not be work properly. Okay, so again, this one I tune at 0.01 and 2. So it will give me this, you know, if I operate within this range, okay, it should be okay. All right. Okay. All right. So these are the buck boost converter. Now, mostly you will see buck converter or boost converter are commonly used in many commercial. Buck boost, not really. Okay, not really. Okay, so we come to a summary. Okay, I said it provides output with voltage polarity reverse without using a transformer again. Okay, then it can buck step up and step down. Okay, using one converter. Okay, the input is discontinued and high peak current again because of short circuit, right? The high peak current, okay, that is flow through a transistor, meaning that your transistor required to have a higher, can be withstand a higher ampere compared to buck converter. Okay. All right. Like I said, buck boost rarely used in many commercial product. I hardly find any. I do see some buck converter. I mean this MPPT lah. Okay, for this what we call this inverter. They use buck boost. Okay, they do have lah. Okay, but not many, not common. For buck converter, commonly used or what we call this charge controller. Okay, the charge controller for this. Okay, maybe I can show you. I mean, I think I already show it somewhere. I mean, the buck converter part lah. Charge controller commonly used. Okay. Okay. Okay, these are charge controller. Okay, standalone, commonly used. Okay, boost is for grid inverter. Okay, up to this point, any questions? We basically already cover the three most fundamental and basic DC-DC converter. Any questions?
No, sir.
Okay. Okay, so now we will move on to the flyback converter. Okay. After the buck boost, we go to flyback. Okay, flyback converter, all right, it provides insulation through high frequency transformer to step up or step down. So it is, in other words, okay, it's an insulated version, okay, insulated version of a buck boost converter. You can do step up, you can do step down, but with the use of high frequency transformer. Still we need transformer, but high frequency transformer. Okay, now flyback converter is basically, like I said, it's just like a buck boost. Okay, this one will have real application. Okay, so how is it? Okay, as we know that the boost converter, buck converter, and buck boost, they are not, there's no insulation, meaning that anything wrong here, let's say your diode or short circuit or whatever, you know, the power will just short over there. It will damage your load. There's no insulation at all, right? So which is very dangerous. Okay, it depends on application. Okay, so for some application, okay, if insulation is required, okay, then it is dangerous. So let's see. Okay, again, you can see this is the buck boost converter, right? The transistor here. The inductor and the capacitor are in parallel and blocked by a transistor. So how this insulation, okay, took place? First of all, you will use the couple inductor. Okay, instead of just a single inductor, right? You use a couple inductor. Okay, so there are different names from different textbooks. Some they refer as high frequency transformer. Some they say no, this we cannot call it transformer, we call it couple, okay, inductor. But anyhow, it provides insulation. means that any short circuit happen here, right? The current will not propagate through. Okay, so it provides a good insulation. Okay, so by changing this single inductor, okay, you get the couple inductor. All right. So this couple inductor sometimes, right, they also look quite similar, okay, with the what we call this inductor. Let me show you couple inductor.
Sir.
You sharing browser? You know, you're sharing a browser, is it?
I'm not sharing yet. I okay now here. Yeah. Couple inductor.
Oh, okay. Just checking because I think this one you show us the.
Yeah, I got two screens. That's why I sometimes I don't know which share screen I'm. Okay, now the couple inductor may look something like that. Here's a very good example. You see, it looks like inductor, but be careful. You see, there is a primary coil and a secondary coil. When you look at this is a couple inductor, or sometimes they call high frequency. Okay, what we call transformer. It's not the transformer that we use to step down 240 to 12 volt. Okay, so symbol will look something like that. It's a symbol wise it look like transformer. Okay, so this is what we call couple inductor. Okay, so after that, okay, they put a transistor moving instead of at the positive it moving to the downward. It's still the same. When it turn on, right, it will charge. It will charge this. Okay, it will charge this. The dot here, okay, indicate the polarity. Okay, the dot here indicate the polarity here. Okay, so of course this one move over here, then this one become positive. Okay, otherwise it will be pointing here. So you will sometimes very confused. See how come the diode sometimes circuit show some is show here. So it's because of the polarity. Okay, so you see first step buck boost. Use this one to provide couple inductor or high frequency to provide insulation. You just change the place. Okay, polarity no change, but you change here. And then this part here, okay, it become like a rectifier already, right? A half wave rectifier, something like that. Okay. And the rearrange to form the flyback. Okay, so this is how a flyback inductors come about. Usually textbook that show you flyback like that, and you had no idea how come it is a relative of this buck boost. Okay, this is how it comes from. Okay, then when you turn on, right, you turn on again, this will charge. Okay, this will charge. All right, turn on state. Okay, it will go and charge. Now the difference between this couple inductor or high frequency transformer and the low frequency transformer is that couple inductor have the ability to store energy. Transformer cannot. Transformer 250 in, 12 volt out. There is no energy store. Okay, it just in out immediately. There is no energy store. But for couple inductor, they are energy store. Okay, they are energy store. So it will charge. Okay, and then discharge. Okay, so it will charge, store an energy, and then transfer over. Okay, it will transfer over. So during the off state, now if it's on state, right, it will not transfer over. Only the off state, it will transfer. So that is a very small moment of time. Okay, so it's now it store energy and release over here. Okay, and release over here, like show here, it start to discharge. Okay, discharge. All right, so again, charge. Okay, if I keep on, if I keep this thing on, it will not discharge. The energy will store here. Okay, but the moment I off, okay, then the energy will discharge. Okay, so there will be energy store here, store there. Now, for the normal transformer, why it doesn't store? Because you're applying AC in, right, 50 hertz. Okay, so it's continuous. Okay, there is no duty cycle for sine wave, but this one you can control duty cycle. And okay, after that, okay, with the inductor equations, okay, so this is just to show the derive, the on-state current, okay, the off-state current, and then to find the duty cycle or the V out, okay, is V in and your duty cycle divided by D minus 1. What is N? The difference is that the N is your transformer ratio N. Okay, it can be 1 to 2. Okay, this will help to boost. You will 1 watt in, 2 watt out. Okay, it will help to boost by using this transformer. Okay, or maybe step down. Okay, 10. Okay, to 1, for example. Okay, so even you have 100 watt here, you don't need to worry. You end up here only 10 watt. Okay, so it depends on how you want to use it for. Okay, and it provides insulation. Okay, it provides installation. Okay, so there will be an N, okay, as a factor. Of course, if you use a transformer, the ratio is just 1. That means there's no step up, step down. Also can, but very rare. Usually they will have some ratio over there. Okay, so here just some idea about the gain. Now we talk about the gain. So the gain, okay, you can see the duty cycle, right? Okay, the gain difference in terms of the N. Okay, N equal to 1, the gain is here. If your N go lower, 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 then it will move up. This is the line of the gain, okay, of the flyback converter. So flyback converter usually operate at this range, again, 70%, maybe to 95%. Okay, we operate at this range. Okay, now we look at the most important component, which is the high frequency transformer or couple inductor. Okay, now this is how it looks like. Okay, always they're labeled in yellow color if it's in the transformer form. Okay, when you open up, you see this yellow transformer, so bear in mind, it is a high frequency transformer. That means it works in square wave, not sine wave. Okay, because the switching here, when we switch it DC, right? So you are actually having you are having a square wave, right? A square wave to apply to it. So it's not our ordinary step down transformer. Okay, so turn ratio provide either step up or step down. So they are in many forms. Okay, you will see this most in the power supply system. Okay, so why high frequency? Okay, if we look at this transformer size, okay, now 50 to 60 hertz low frequency transformer. Okay, these are the size. The higher the current, the bigger the size, the more heavier it is. Okay, but if we are using the high frequency transformer, it can go as low as small as this one. You can see compared to all these 4, 1, 2, 3. These are all the low frequency transformer. Okay, typically they operate 20K to 200K. Okay, for the reason of reducing the size and weight. Okay, frequency increase. Remember, the smaller the inductor you have, the smaller the transformer you get. And then where do this thing apply? Okay, now these are the old days transformer, 50 hertz, 60 hertz transformer, right? When you open up, it is very heavy, and there are a 50 hertz transformer inside there, and the 230 watt go in, and then 12 watt go out. Okay, you can still see some of our old days, charger and power supply. But nowadays, when we open up our new charger, okay, we open up, you can see so small. The transformer here so big, and the transformer here so small. Then we know that, oh, this is the flyback. Okay, high frequency transformer with a switching, okay, transistor. Okay, so this is how our handphone charger are made. Okay, they are using this high frequency, so it becomes so small, so light. Now, to do that, okay, first of all, if you want to model this, right, we first have to model the couple inductor. Okay, this one is not available in MATLAB, but you can actually model them. Okay, using ideal transformer. Okay, you can model using ideal transformer. Okay, you get the ideal transformer, and then you have to connect a parallel inductor. Okay, because it's not 100% transformer, it's a couple inductor. So we need to have a inductor, okay, in parallel, and then we measure the current, because these are the current of the inductor current. Okay, and then of course these are the secondary, these are the primary. So you can make a block. Okay, you can make it a block. Once you make a block, right, you can do that. You can put a picture there, then you can model this, what we call this high frequency, okay, transformer. And then of course you can have a N ratio, okay, N ratio, which is your winding ratio, okay, and then you can add the inductor, okay, of this. All right, now normal transformer, we only know the ratio, right? But there is no inductor element there. But for this couple inductor, there is a, what we call inductor element. Okay, so in order to do that, you need to create, okay, your own couple inductor. So now okay, this one is the model. Okay, so today we are going to do this one. Okay, now we have a 12 volt in. Okay, and then we're going to, put a transistor. Okay, and then go through the couple inductor. Okay, and the couple inductor output, okay, we put a diode. All right, and then of course when the diode negative here, so this one will be a negative lah. So if you want to remove it, it will become positive. So we will take the output, okay, this capacitor and the resistor as a load. Okay, okay, this is no feedback yet, right? You just simply control this one, and then you will have your output. Okay, of yeah, I think the calculation will give me 11. You need to do adjustment. Okay. Okay, so here I will show some of the parameter setting. Okay, I applying 20 okay hertz. Okay, and inductor value is 1 milli, 47 and 12 volt. Okay, so if everything is run correctly, okay, so you should have this output. Okay, you should have this output. All right. Okay, now we will look at, like I said, even the commercial power supply, right? They already have the chip that can help you to do that. Okay, what you need to do is that you just need to buy this couple inductor. Okay, the couple inductor, okay, and do the what we call the power supply. This is how our power supply are designed. Okay, so okay, this is another example. Okay, you see where to get the 12 watt. You see, in fact, right, they are actually applying, 230 watt, and they go through a bridge rectifier. Okay, and then come in here and step down, then you will get like 5 volt or whatever voltage that you want, okay, for your power supply. Okay, so okay, this is another example lah. Okay, we can do a feedback control for our USB charger. Okay, maybe we will do this one first without a feedback loop. All right, slowly, because we are almost done already, just to get this finished. Okay, commercial application of the flyback. Okay, here is 230 or 112 lah, depending on which country you are. Right, you will have a rectifier, you have a filter. So you will have around like 300 watt here actually. We have around 300 watt here. You can directly connect to this. Okay, this is how our, like say like our charger is made. Okay, and then we switch them. Okay, we switch them, then we get the output that we want, 5 volt, for example. Okay, because this is our power supply for USB charger. This is exactly how our USB works. Okay, and then of course I can connect to the load with a USB plug. And the output of this 12 volt will get into, not 12 volt, the 5 volt will get into the feedback. Okay, again the PI, okay, PWM, and then go and control this. This is how our charger was made. Now, how much power your charger can deliver, right, is depend on this transistor and this transformer. So nowadays, the fast charger, how many watt? Any one of you know? As far as I know, it's 30 watt, 33 watt. 33 watt can charge from 0% to 100% in 30 minutes, right? In 30 minutes, so from 0 to 100. So it's actually depend on how large the power you are. The pasar malam one or the one that you use in your car is only 5 watt. Okay, it's only 5 watt. Okay, so you look at it, okay, this one is actually around 5 watt. You can easily get it in pasar malam. Okay, this one maybe 10 watt, I'm not sure. Okay, so these are the commercial application. When you open up, right, it's actually a flyback. Okay, or some they have this built-in, okay, in the the power socket here. Okay, so now the advantage of using of this power electronic converter is, in the old days, we will need a transformer that have 230 watt input or 110 input. Or the device, right, you need to switch to change, okay, the power input or the frequency. But with the advancement of the power electronic, right, we no longer need this one, no more. This one, no need. This one also no need. Because, okay, our DC-DC converter can do all this job. Okay, smaller in size, lighter in weight, higher power density, and you can bring around the world, widely used commercial, right? Because you can see these are the world map. In the old days, right, if you bought something from Japan, you cannot use in Malaysia, right? Because the voltage different, frequency different. Nowadays, we no longer have this problem, okay, because of power electronic, right? When you have all this DC-DC converter in place, we basically solve all these problems. Okay. All right. So, okay, maybe let us start to do this very simple model, okay, by following the slide here. Okay. Let me see my model. Is it still around? Flyback, 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 flyback. Flyback converter. Okay, flyback converter was last year assignment so this year you're all doing grid connected. Open load, where is it? Where is it? Okay. Now, if you all don't want to do the model there, you can actually do it here. I mean, you don't block it, you can actually do it here. Okay, if you think that you don't want to do this model, want to put picture, like you create your own this one, that's fine. Okay, you can actually just do it, put an inductor, okay, put an inductor, 1 milli, and you get a transformer, okay, ratio 1, okay, and then you just connect like that, it should work lah. Okay, let me try run. Okay, yeah, 11 volt. And you can see the voltage and the inductor current. Okay, so inductor current. All right. So, okay, let's say I try to, change the duty cycle because I put 50% ma. So 51%. Okay, 51% now is 11.5. So if I want 12 volt or maybe 5 volt, okay, if I want lower, of course, this one need to be smaller. Lor. Okay, 40%. Yeah, because my transformer ratio is 1:1. Okay. Okay, now I want to, 7 watt. Okay, so now class, try to do this. Okay, you no need to do the model unless you got time. You can follow the way this transistor node changes. This one is the same as what I show. Okay, it started is 50% now, but I want you all to find the value that you can achieve 5 volt output. Okay, so this is the typical your charger lah, except there's no AC lah. You just need to have the AC and feedback later. But now we do this one first. Okay, it's the most fundamental. Okay. Okay. Capacitor 47. All the value is in the slide already. Okay. This one I put 12. And okay, where to find this? Okay, this transformer, right? Okay. Transformer, SimScape, electrical. If I'm not mistaken, is here. Transformer. Okay, linear transformer. Where's the linear transformer? Not the mutual inductor. It's a linear transformer. Oops. Then it should be here. Foundation library. Okay. It's under foundation library electrical element. The ideal transformer is here. Okay, you can move it over. Okay, this is idea. When you click, right, there's only one thing to change. It's only the winding ratio. Okay, so this is the ideal transformer. Don't confuse with the mutual inductor. Okay, there's a mutual inductor here, right? Okay, so this mutual inductor. Okay, the mutual inductor, the problem is that you need to know the L1 inductor, the L2 inductor, and then the coefficient of coupling. Okay, so it's very different. Okay, this one you just need to know. Okay, the ratio winding. Okay, try to do this now and show me the output where you can achieve 5 volt. Okay, tell me the percentage. Okay, how much? Just now I put 40%, right? I achieved 7 something already. Oh, 38%, 32.5. Okay. Oh, super fast. Wow. Good. $32.5. Okay, let me try. 32. Like I said, when you have around 50, right, the buck boost, doesn't increase or decrease. So, okay, let me just run for 0. Yeah, I get 5 watt. Okay. So come class. Yeah, I ask you all to do this because at least this one is something really useful and it has been used in many of the commercial, I mean, the charger you use today, I mean the house, you open it, I guarantee it's the Flyback. The only difference is the transformer they use, okay, and Now, what makes those branded so expensive? Because of the quality of the transformer, for the transistor as well, okay, they use, okay. Okay, very good. Okay, got 2 students got it already. Oops. Okay, let me just bring this over. So we will get this DC-DC done. Okay, Osama. Okay, good. Okay, so you know how to create your own, high frequency transformer. In fact, this type of Flyback, right? If you type inside Apple charger, so expensive, right? Who own an Apple phone? You can see that right? All these charger is, you will see a Flyback transformer. And of course, the counterfeit one and the real one difference. Okay, when you open all this, right? You can see this is all inside. All these are our charger nowadays. Okay. It always has a Flyback, some switches. That's why it can be so small. Okay, so small. And this one, counterfeit and an iPad. Okay, so it's the quality of the transformer. Okay, of course the original one. Okay, if you go into the website, they will actually explain. Real and counterfeit iPad charger. Okay, so this is the original one. You can see that first of all, you see the capacitor they use is bigger, means higher wattage. The capacitor they use is smaller wattage, and this is the Flyback transformer. The size, and this is the real one. Okay, counterfeit. Okay, the left one is original. Counterfeit is the right one. But be it left or right, I mean the operating principle is the same, but the component quality will be different. Of course, it will affect the performance as well. And like I said nowadays, right, all charger okay, you just put a phone charger or you just put inside. phone charger. Okay. That one will include many brands lah. Okay. This is what's inside lah. Okay. How you look at this, you know it's very low quality lah. HS, high frequency transformer. You know there is a rectifier. You know some switches, feedback, and the diode. See. Okay. And then yeah, all those will open up, right? High frequency switches. Okay. High frequency switches. Yeah. And also even the old phone charger, okay, when you open, see. So these are okay inside of a phone charger. All right. So yeah, this is the most widely applicable DC-DC converter nowadays lah. I mean, almost 90% of the charger circuit, right? Okay, are using this flyback. Okay. Because of the ease of use, okay, of this transformer. Okay, you can actually buy this transformer. There are data sheet around. Okay, there are data sheet around. Let me find. Because for last year the assignment is to make this lah. That's why I also didn't put it online. Let me see. Do I have this information? The problem with the high frequency transformer is not easily available. Okay, in the market you need to really go to like, I mean, Jalan Pasar is very hard to find. Okay, you need to get it from Element 14, those official shop. Okay, only you can get this type of transformer. And because of they are making this transformer usually for a batch of charger. Okay, especially the N value, it's a bit hard for you to get the N that you want if you want to design one yourself. Hardly can find a good data sheet on this. Okay, I need to find one. I remember because last time they're using assignment, I do provide them a few industrial data sheet. Okay, so that they can actually make their assignment. Okay, let me find it. I'm not sure I'm still keeping it here or not. But in AliExpress, this type of place is you can find quite a lot. Okay, in AliExpress. Because most of the low cost flyback transformer, right? They are actually getting from there because they sell in batches and it is very cheap. Infineon DC and PC. And apart from the charger, right, what we see here, it is also commonly used in the computer power supply. Computer okay, something like that. Okay, our computer power supply, right? When we open up, right? Okay, high power See, you will see a lot of copper inductor, okay, and high frequency. Okay, it's also widely used in all these power supply, okay, for high power. because this one, easily 300 watt, 400 watt, right? Compared to the one that we have 33 already considered fast charger. Okay, you can see our power supply, okay, computer, laptop, power supply, they are all in this configuration. Okay, they are all using, of course, with PI feedback, lah, so they can always maintain a very good control of it. Lah. So computer power supply is one of them. You can see they use this, flyback topologies. How to control a subsystem? You don't need to control, you just need to fit in the value. Lah. Yeah. Unless you create a mask law. Okay, so we have another one done already. Okay. Okay, good. Okay, so this is one of the example. In fact, right, in Plex, they also have this example for you to, to play around. They do have this inside Plex, a complete power supply. Okay, let me see. Okay, you go to demo model. Okay, in Plex, it actually have a lot of ready-made lah. Okay, circuit for you to Plex demo model. See basic topology, our boost converter. See, it's already here actually. Our buck boost converter. See, our flyback converter is all here. See, the flyback is the same way, they model the flyback. See, and then the good thing is that you just click open model. Okay, here we go, example circuit. Then you can play around with it lah, the flyback. Okay, and then you can run. Okay, see, super fast. Okay, so there are a lot of basic topology for you to play around. H bridge lah. Okay, all these are actually here. Even need to power supply. Okay, buck converter, boost converter, power supply. This is the power supply for how to do the power supply with thermal model. Okay, power factor correction, 300 watts. This is the computer power supply. This is the real computer power supply. And then you want to know how it works, right? Click this one, then the model pops up. Then you can learn how they do a thermal analysis of this 4 diode. Okay, then you can learn how to apply it to your assignment. Okay, so a lot of things you can learn here, all right, for the Plex. And they are PDF for you and explain everything in detail. Okay, how to do that. All right. So this Plex is not just software lah. It also a set of power electronic textbook here already. Make good use of it lah. You can download all the PDF before the license expire or before you graduate. So you can refer it for your future use. All right. So this is Plex. Okay. So maybe now we will move on to. Okay. So when you get this done, okay, I don't want to save. Okay, so now maybe we will do a feedback. Okay, a feedback control. All right. So okay, what I did here is actually I put to measure the power lah. Okay, so maybe I'll open my model for you to see. So this is much more a complete circuit. That means I can put 240 watt, 30 watt here, right? Okay. Let's see. Wow, I'm not sure it's still here or not. Oh, it's still here. Oh, good. Okay. All right. So now, okay, you can do this model. You already done this part, right? So what you need to do is that you just put a full wave rectifier here. Okay. You just put a full wave 325 peak. Okay, here. And then this one I model EE16. This is the code of the transformer. Okay. EE16, the ratio is 11 to 90. And the inductor is 0.8 milli. So the inductor, you put 0.8 millihenry. Ratio is 11/90. Okay, this is the real EE16 HF transformer. Okay, the rest I think is quite straightforward. Okay, this one's 47 microfarad. And then, okay, this I put 2.5 ohm. Okay, you can just change your one to 2.5 ohm now, because here I also measure the voltage and current, and I calculate the power lah. That's why I want to show the student like how much power I can, I can design. And then again, you just take the wattage. Okay, the wattage got feedback, right? I want 5 volt, okay, and then the PI. Okay, show you what is my PI. Okay, my PI is 0.05, P is 0.05, I is 0.8. Okay, and then PWM. Okay, still same lah, 20 kilo. The one no change. So let me just run this. Okay, so I have 5 volt, 2 amp, and that means this is a 10 watt charger. Okay, it's a 10 watt charger. Okay, try to do this one. Okay, I'll leave this on so that you know the value of the inductor. I'm not sure I can open this or not at the same time. Oh, cannot. Oh, it won't show. Okay, the P and I value. Okay, important is this one. Let me find the EE16 transformer. So any value you need to know, please let me know. Of course, this value I obtained from data sheet for this EE16, the real flyback transformer. With a PI, you should be able to do a nice charger. So this is the most fundamental one. Okay. You can try Google to see this high frequency transformer. Okay, there are plenty of it. Okay, EE like 16. You can see they actually have many of them, like this one, AliExpress. This is how it looks like in a real transformer, 10 watt. All right. So let's see. It's actually not very expensive. You see, it's 166, 100 piece. Okay, it's not one piece. 100 piece means that one piece only 1 ringgit, 60 cent. Okay, so of course, yeah, you can make big money lah. Yeah, this is how where I get the data. Yes, this is the right one. Okay, it will tell you the primary inductor is 0.8, and the turn ratio is 90 to 11. Okay, so this is a symbol, the size. I mean, if you really want to design your own one, right, it will give you the footprint and so forth. So this is, yeah. So, okay. So from here, this is how I put here, 0.8, 11, 90. Okay, ratio. All right. So, yeah, output is 11, input is 90. Okay. So after that, yeah, of course, this is 200. That means it's an AC from your wall socket. You just need a simple rectifier will do. Okay, and then the rest, this will do a job. Now, the importance of insulation is that, you see, in case you got any problem from the AC, right, short circuit or whatever, it won't blow your handphone because of this, okay, insulation. Imagine if you are using a normal buck or boost, no insulation, right? Anything wrong, 240 will go into your phone. Okay, your phone explode. And also there are some cases okay, in the news that people get electrocuted while charging the phone and talking, right? That is also the problem of the charger. Okay, if you want to use cheap charger, make sure you don't hold it while charging. Okay, so the original one will definitely have a very high standard, a good high frequency transformer with a good insulation, so that it won't have. That's why the importance of this insulation is here for real application. Okay, let's see. Okay, the Abon Hong. Oh, still not feedback yet lah. Wow, is it so challenging to do the feedback?
Tuning the PID now.
Oh, okay, no need to tune I show you the value already,
Yeah, 0.
Right, 0.05 and 0.8. Yeah, you should be able to get a good output with these two values. Yeah, you are free to tune now because I also tune manual. So yeah, you should be able.
I got different. I got 4.219 watt after following your PI value.
Oh, okay. Maybe you need a little bit of tuning.
Yeah.
Capacitor value is the same? 47?
Yeah, 47 micro.
Load, I put 2.5 ohm.
Oh, I think it's supposed to be load. I following just now the load.
You put 2.5.
12 is not just following this.
Yeah, because this is the charger. I really design according to the real charger design, which give you 10 watt. I mean, when you buy charger, say, wow, this is 10 watt charger, okay, or some watt fast charger. I actually follow that. Okay. So that you can reproduce this one, see, because this one is a 10 watt, yeah, maximum output 10 watt 10 watt charger is for 10 watt charger. Yeah. So that 10 watt charger meaning that the moment you plug in your phone, right, it will deliver 10 watts with that power. So the PR is still according to it. It's just like a 33 watt fast so-called fast charger we have for our iPhone or Xiaomi or those fast charger thing They are also designed according to this with the PI. Can we see the inside the charger? Can. Inside the charger is just a resistor. Okay. A resistor, current, and a voltage. And then I take the voltage and current multiply and get the power. So I will have voltage, current, and power. Yeah. So I will have a measurement output. I can have the voltage 5 watt, 2 amp, 10 watt. And of course, I need to take the voltage output, right, for the feedback. Okay, so that I always have a 5 volt output, regardless of the change of the AC. That is the important part of this power supply. So even though I change the voltage here, right? Okay, 170, 60 hertz. Okay. You see? I still get 5 watt, I still get 2 amp. Even though now I fly to US, I fly to US, the voltage go low and frequency change, right? It doesn't affect. So this is what we call world power electronic worldwide charger already. Then I bring back to Malaysia. I change back to 50 hertz, 230. I mean, in other words, you go any country around the world, your charger is universal already. It will still get you. This is the beauty of this, design. Yeah.
Oh, so for like the buck and boost, right? They cannot do cannot behave like this, is it?
Buck and boost, not say cannot not as good as this one, no. Because buck will only step down, boost only step up, and it doesn't provide insulation. It can at some way not as good as this one, because imagine if this is no good, your handphone charger are using this one, can trust or not? So many years already, can, right? Our computer power supply are using this, and you bring to other country, you no need to worry about this, this is the complete. In fact, this is a combination of two converter This part is the AC to DC right? Which I not yet teach but you already know. And this part is the DC to DC converter. Even though you put a buck here, right, it will work. The only thing is that there's no insulation. That means there's no guarantee of safety. Okay, you may have some AC flow through your phone, or you get electrocuted, I don't know. That's why I always have this one. Yeah. And very rare power supply, they use boost because you already got 330. What you need is 5 watt. You don't do boost, right? So it's either buck, okay, or this flyback And of course your important factor is your PI right? Your PI control must be good enough. Like you see here is 325. I reduce to half of it, my PI still can handle to give me the 5 watt output. Okay, so basically this will conclude our DC-DC converter chapter. All right, maybe I will do a bi-directional if we got time now, but I still need to move on to AC already Okay, and then Sama. Okay, good. You just design yourself a 10 watt, okay, power supply. So you just change this one to a higher power, then you get yourself, you can make yourself a fast charger. So far, I think in the market is 33 watt, right? Anyone know, is there any higher? I'm pretty outdated, I would say. You want to beat the fast charging, you just, of course, the problem is this You have to tell the factory that make this transformer, say, I want this transformer with this ratio and with this one. Oh, Alan, okay, 120 watt is the highest nowadays From which brand, Alex?
Xiaomi.
Oh, Xiaomi. So how fast it can charge from 0 to 100%?
I think 20 to 15 minutes. Depending on the battery, your phone battery capacity.
Yeah. It's the same theory lah. The higher the watt, right? The faster it go lor. Okay, so 120. Wow, I really outdated leh. But still, you can see the transformer size remain almost the same, right? It doesn't really grow big because of the power. Okay, because they use high frequency. And remember, now we're only using 20 kilohertz. If I want high power, this thing may grow big. I want to make it small, I increase the frequency. And because it's only 10 watt or 100 watt, the losses doesn't really matter lah. And of course, you need to wisely choose the transistor and of course this diode lah, to make sure you have a higher efficiency. Yeah, of course, to measure the efficiency, also the power input here, okay, over the power output here, then you can find it. Mostly will be around 90% of efficiency lah. So, okay. So I hope the last part of DC-DC converter is useful to you, or the knowledge lah. Okay, I teach, okay, for this one, and we do some practical, okay, on this one. All right. Okay, 6:30 already. Wow, so fast. All right. Any questions? We basically done, okay, on DC-DC converter. This bidirectional, I'll keep it until, if we finish everything, then I will come back here to let you know how we can do a bidirectional. Any questions?
No, sir.
Okay, good. So, okay, so we pretty much cover the DC-DC, like I say, DC-DC converter, the basic one is always, okay, these four lah. Buck boost, and we know that the installation version of buck boost is actually flyback. Okay, it's actually flyback. And of course, these are separate, okay, a bit complicated to explain here. Okay, half bridge bidirectional, like I said, the last one, if we got time, we will talk about it. And our double active is even more advanced. Okay, DC converter, usually used for high power battery energy storage. But those commercial one, flyback so far is dominant in the market, I would say. Okay. All right. In fact, as long as you know these four principles, the rest is quite easy for you to understand already. Like chuck converter, right? If you type these topologies, right? If you type chuck converter. Okay. Okay. Okay, you will see the topology is more or less the same. Always got one transistor. Okay. Chuck and Sepik, they will have two inductor instead of one. Or they have two inductor instead of one and two capacitor. Okay. So it's a second order system lah. Sepik also. Okay, Sepik. Okay. Okay, Sepik. But there is always one switching transistor. Okay, there are two inductor, two capacitor, one this one. Okay, it's a second order system. Okay. But the rest, the rest buck boost, all these are the basic principle lah. Okay. Oh, need to be, week 10 already. So a bit rush lah, but like I said, as long as I finish all of them, the required one, then if we got extra time, we will come back to those I may go too fast, or we miss those like exercise to, ask you all to do, the model here lah. Okay. So, all right, any questions? Okay, so if no questions, we will end the class today. Thank you.